Good afternoon. I'm very happy to be here in this meeting and want to thank the organizers. Very happy to close this very interesting day and very happy to present the first experimental talk. So this will be real measurements for the good and for the bad. These are the excellent students who performed all the things, all the work I will talk about. And Omri Shaltiel is over here. If you find this talk interesting and you want more details, he's the guy to approach. So, some background and context, because I understand the audience is broad. And I will talk about turbulent flows in strongly rotating system. They will be deep, not so much like this. I will explain and define these things. Such flow, the relevance is in engineering, but also in geophysical flows to some extent, in some limitations. And we want to understand them better and to answer some questions as for what are the principles that govern some of the pronounced phenomenology of such flows. So I will explain what we see later. This is a vorticity map measured in a 3D volume represented only by 3 representative horizontal planes and 1 vertical plane. And I will talk about what is the range of flows we consider. I will present inertial waves, which will be the main actor in this talk. Describe how we approach and how we try to get information about what's going on in such flows. And then I will, mainly try to get information about how energy flows in all relevant spaces, real space, frequency space, length scale space in such systems. The relevant equations which we already were mentioned here in different contexts, Navier-Stokes, rotation here adds this Coriolis term. I will consider incompressible flows. And in addition to the Reynolds number, it was already mentioned, we have the Rossby number, and we will talk about a case where the Reynolds number is big, it's turbulent, and the Rossby number is small, the rotation is very dominant. And I will talk about systems that are deep in the sense that this aspect ratio is order 1, it's close to 1. They are not shallow layers. And yes, we will see that the attempt we are doing is to put and try to put a rough picture of how to talk simply about such flows. And every time we hit a problem and something doesn't fit, and so we try something else. And I don't promise there will be a happy end to this. Okay, very, very crudely and in a way just to get started, main observations in strongly rotating turbulent flows is that large scales like vortices that we saw, sometimes even condensate system size structures are formed, very reminiscent of 2D turbulence. If you do measurements, these are old measurements that, and probably they are older, showing that indeed there are strong correlation between in the z directions. It is close to 2-dimensional flow, but there are some things that would not exactly fit. Questions about energy spectra. And let's say, even without considering the details of these specific examples, 2D is useful, apparently, and it is. but how it becomes 2D, how energy goes from 3D to 2D, and how things can stabilize on a steady statistics. Inertial waves. We heard about them before, and if we take the rotating Navier-Stokes equation and we linearize it, then there are solutions of waves that these are helical waves that propagate due to Coriolis acceleration, and I will only discuss their dispersion relation, which is funny and interesting. The connection between the frequency and the wave vector is given here, and the main things that we will kind of use are these. First of all, there's a cutoff. Frequencies that are larger than 2 times the system's rotation frequency simply would not excite and propagate as waves. And if I get into more details, then there is a relation between the frequency and the orientation of the wave with respect to the axis of rotation, not its magnitude. It was mentioned earlier, but it will be useful and be used in this talk. Some other details about group velocity and phase velocity, which will not be of importance today. Okay, so we have the nonlinear equation. When it is linearized, there are waves. These are these waves. This is their dispersion relation. Okay, let's go forward. So can this 3-dimensional flow field that we saw, which was very messy laterally, and as we saw these long correlations vertically, can it be described as a wave turbulence of those inertial waves? And if so, how those waves lead to this quasi 2-dimensional state, and how do they interact with it? Questions that we already heard yesterday and today. Just about wave turbulence, without getting into the details of specific variations of theoretical modeling, but systems, nonlinear systems that develop turbulent state in a sense of a broad spectrum, continuous spectrum, universal one. But their linear modes are waves. Sometimes, and this is an example of capillary water waves, elastic bending waves in a plate like a gong sound, and internal waves. Sometimes they would develop the turbulent state while leaving, not diffusing, anti-diffusing in a way, not living here, but living along the dispersion relation of those linear waves. And the question is whether our system belongs to this family. This question was considered earlier and by many people, and experimentally there were observations of inertial waves in rotating systems in non-turbulent flows, but also during the build-up of a turbulent state. And recently there were more. I will mention the more recent works. But overall, there's a need for experimental data from those systems in order to check if and to what extent and in which way wave description is useful for those flows. So our experimental system is sketched here. It is a big tank. These are the dimensions here on a rotating table. It can rotate very fast. So these are more than 600 liters of water that rotate in frequency of more than 2 hertz. And we measure, there's a pump, strong pump, so we have a broad range of parameters, both in injection, in rotation, in Rossby, in Reynolds numbers, and the big separations between the scale of injection of energy and the system scale. So the system can develop freely until reaching the system size. There are many outlets I will show it, that generate jets and inlets. So overall, if we balance well the system, we inject nearly only small scale without large scale injection, which is experimentally, it's a difficult task to balance a system and to have a clean injection in wavelength. And we measure we do PIV. Here we present a single layer. I will show a variation in which we can measure a volume. This is a photo of the system, and this is the bottom. And now let's see what the experiments are.
Does your system have a rigid lid?
Yes, yes, yes. Here there is a rigid lid, flat. It is made in order to be able to insert a beta plane as well, but we were stuck with a flat lid, and yes, it's important. So experiment 1, build-up of turbulence. We bring the system to solid body rotation, meaning pump doesn't work. We rotate for a while until this block of water rotates with the system, and then at a certain time, we make a step function and start injecting energy. And that's it, and we measure the velocity at a given height above the injectors, the given plane. So this is an example of the vorticity oops. Let me see, does it work? That's strange. I think it should work.
Go ahead. There it goes.
Yeah, it works. Okay. Okay, sorry, now it works. So first we see the injector symmetry, but very quickly those vortices start interact, they merge, they will slowly develop into a different, more uniform state. Somehow I don't see the slider here. I wanted to accelerate this movie, but I will not. So eventually we see the formation of large structures. You see merger of vortices, of cyclones, and so on. And this is one plane, and we study this horizontal one plane of the flow currently.
This middle plane, Eran? Which plane?
Sorry?
It is a middle plane.
This specific one, I believe it is like 2/3 above the injection. But there's a very weak variation of those fields before you get very close to the injectors. So if I make a map of the energy density, the kinetic energy in the plane, this is a cut. This is this 80 centimeter cylinder. So 1.3 seconds after turning on our pump, still zero energy. Solid body rotation, the flow is completely static. At a certain time, energy appears uniformly across the plane with a delay. And later on, it becomes more and more intensive. And only about 100 seconds later, we get the steady state with, you see the large scale structures that are formed. So it feels like, smells like inverse cascade. Let's see. So the evolving spectrum in time, the thing that we just saw. So in 2D turbulence, this old work that showed the build-up of the K-5 spectrum in really 2D system. We see the injection of energy, and over time, we see the filling up of a spectrum all at a given time to a point which can be defined as K star. And this K star migrates to the left as we put more and more energy into the system in a specific way, with this specific relation to time and to epsilon, the injection energy. So what happens in our system? This is two-dimensional system. So this very similar thing happens. Injection, early times, build up of the spectrum up to a point, K star. We can measure this K star, and we find that it propagates with this power of time and with this power of epsilon. So in a sense, yes, the system shows inverse cascade even like quantitatively. Good. So let's, however, look at this the same process, the same data set, and we just plot time here, energy here, and this will be the wave number. So all vertical slices are plots of the energy spectrum in a way. So we see the inverse cascade. We inject here, and over time, energy goes here. So this spectrum here is very different than this injected spectrum here. But if we zoom to this very short time, when energy arrives, this is what we see, with a clear slope here, that every wave number arrives at a different time to the measurement plane. I will not spend time on it. We analyze it, and we can show that this time is exactly the traveling time of inertial waves from the injection plane to our measurement plane. So apparently all the energy that we inject into the system, and this is strong driving, which evolves into a strong turbulence, is carried by inertial waves, those modes that are linear modes of the system. Related and very similar observations were made before us, with everyone contributed some detail to this observation. So waves carry the energy, but what are they important in the steady state of the system? So now we will search for waves, remembering the cutoff in frequency and this dispersion relation frequency angle. So we measure the velocity point-wise and Fourier transform it in time. So it is a temporal energy spectrum, like what you would do with hot wire probe or something like this. And we can define the energy, and this is what we get. Frequency, energy, and these are different experiments in different rotation rates of the system. So, first of all, we find a very robust power law here, which is about minus 4/3. Omri now correct me, and this minus 4/3, don't take it strictly. It could be that under more careful driving of the system, it is actually minus 5/3. But this robust spectrum holds. So we see this spectrum, which we don't know, and I don't know of predictions of this specific scaling in frequency. It goes to very low frequencies, right? Remember that our omega here is order of 10, 15, and we get to minus 10 in frequency without any, while everything continues as usual, which is kind of surprising. When we look here, we see that this power law terminates at different points, and if we flatten the spectrum, we see that these are very sharp drops of the energy spectrum, and they occur exactly in 2 omega frequency. This means that inertial waves are there in the energy spectrum. They are in the steady state. They are there. This cutoff of this frequency is pronounced in this field, in this three-dimensional field. Okay. Now, what about this? This part of this energetic part of the spectrum, which is above the cutoff. Are the waves there? Can we see indications of what they do and how they interact? So in order to do this, we need to have three-dimensional measurements. One plane is not enough because we must probe this theta, this orientation of a wave. And in order to do this, we modified a bit the system, and we have now a rapidly scanning horizontal laser sheet, and we build stacks of a horizontal velocity field, but three-dimensional one. So we can map the flow field in a volume of 30 by 30 by 30 centimeters in a relatively high resolution. And it looks like this. Omri just prepared this thing. We see. Okay, I didn't know you put music. Okay, but this is to wake up everybody. So you could see the rotating and the scanning laser sheet, etc. And now we can do this transform in time and in 3 dimensions, exactly in order to see, like was mentioned in earlier talks, whether our energy lies on the dispersion relation of the waves or not. We define this energy, we go to the, first of all, let's look at this energy, and this we saw before the vorticity, now we can see the energy. And again, we see, first of all, long correlations, long vertical correlations, these tornado or hurricane-like structures, and a turbulent field, which looks turbulent horizontally. We saw already that these horizontal slices, they have this k-5, etc., etc. They are very much to the turbulent. But we see now this 3 dimension. Now, when we try to do this, I would say this doesn't look like a wave field. But let's do it, let's try anyway. So, we move to the relevant coordinate system of theta and omega and average azimutally. And this is what we get. We were very, very happy. It was more dirty data before, but really with no many tricks, this is really what we get. So this is this cosine, 2 omega cosine theta dispersion relation, and this is where our energy lies. So in a way, it's an anti-diffusive system in this sense that energy doesn't live in this broad space, and we will see that it is not just this dispersion relation, it is this pancake here that where the energy goes to. So yes, so waves are apparently important, and we can now modify omega and check whether this prefactor also holds, and yes, it holds. These are different experiments, different rotation rate. Once we rescale it by 2 omega, it goes to this dispersion relation. So the energy in this 3-dimensional field which we saw, which is anisotropic and complicated, lies on the dispersion relation of the waves. Does it mean that it is wave turbulence? No. Here there's a problem which we try to attack from all directions, but it is very stubborn. Let's look at this guy. Yeah. Most of the energy, this is a logarithmic scale in color, most of the energy lies here. This is this point which is 2-dimensional. The vertical, the frequency goes to 0. These are modes that are extended in the z direction. They don't. The waves do not have a z component. The energy is there. It does not contradict inertial waves with vanishing frequency, but it also could be this alternative, this coexisting eddy field of 2D turbulence. And this is exactly the place where we have the least resolution both in angle, because imagine a Cartesian 3-dimensional grid, and and all the energy goes to the origin, and we need now points in order to know whether it is zero or whether it is slightly above zero angle, and also in space. So this is a problem which I believe simulations should have as well, and we have everyone who works on a Cartesian grid will have this problem. But we can go around it in different ways, which I will describe. Okay, so once we saw that the waves are there, we want to map a broad phase space of the flow and understand where waves are relevant, where do they stop being relevant, and then to understand how can we detect energy transport rates and scales in those waves. So first, these are different experiments, different conditions, and you see that qualitatively, in this range, waves are the modes of the system. Excluding, or not excluding, but with a question mark over here. But obviously, this dispersion relation is a relevant information for the connection between time and space fluctuation in the system. Down here, no more. The system, so what was different? We drove the system more strongly and rotated, so Rossby number increases down here, and k, the wave vector, increases this way. So what can we say about these limits? And what can we say in general about what happens here compared to what happens here? We see broadening. So obviously nonlinearities become stronger. Time scales become short compared to frequencies of waves. Let's try to put it together in a way that we can say some meaningful thing about it. So here is, this is not bragging, but I like it very much when I see, and I think we should do more things with it, because we can sit on a mode, on each mode in this ball of k, of wave numbers, and practically measure its evolution in time. So this is the real part of this specific mode with this theta and this phi and this wave. So a point in the k space, and we see it oscillates, and the frequency here is exactly the frequency, or very close to the frequency that we saw of omega of k. And we see slow amplitude modulations of this thing, slow in the sense that there are many periods of the waves in a modulation. And so this broadening of the spectrum is in fact caused by these modulations, which reflect the interaction of this mode with all the rest of the flow. We don't know with which component, but they definitely reflect, they give us the indication for the nonlinearities in the system. So we can measure with delta omega of a mode of this given omega and plot it. So this is what we get. This is delta omega over omega as function of the Rossby number. Obviously, there's no data collapse here, and we spent some time in order to try different ways of extracting a relevant timescale that will describe well this system. I will spare time and not give all the details, but this is the same data once rescaled properly. And this is the relevant time which we extracted from this data for the dominant, strongest nonlinearity in these conditions. We have a good data collapse as long as delta omega is small compared to omega, and it stops as we expect to see when we go beyond the regime where we can talk about slow amplitude modulation, or where we get this messy spectrum not on the dispersion relation. But it means that it is, by the way, it is consistent with a timescale that was reported in this simulation. And I would like to see there it was suggested as a Doppler shift. I don't want to commit that this is the process. I'm not sure I could see how Doppler shift would excite amplitude modulation, but it's not critical. I see it more like a mean field type of nonlinear of interaction. The strong, effective, quasi two-dimensional field interacts with a mode, and this is the mechanism. So kind of a direct interaction between the quasi 2D mode and a given mode. So what is the process? How can we say anything about the process in all these three-dimension time and space? So yes. So yeah, talking about anti-diffusion here. So really think of it. We start with in K-space energy in this big watermelon thing, and we end up channeling nearly all the energy to this small pancake that lies near the origin. How does it happen? So here we start need to be more careful, because it depends on under which conditions. So at very low forcing, and I'm talking for us, it's the lowest we could get with our system. In other experimental systems, and I will show the reference, it is a normal driving intensity. So here we see energy spectrum again of frequency. So this is frequency. Remember that frequency is also orientation. With different experiments increasing Reynolds number. So Omri measured it, and at the beginning you look at this thing and you see this grass here that someone didn't cut it well, it's a noise, and so on. No, it is not. This is the surprising thing, that you can track this. You repeat the same experiment with the same conditions, you get the same noisy spectrum here with those little spikes, many of them. And when you start analyzing them, then Omri picked up, I don't know, 6 different triads, not just of the injected mode with others, but also a second generation. So there's a whole zoo of 3-wave interaction. So we could say that it seems like in very low driving, and it is highly related to this work of Pierre-Philippe Courtet, 3 waves interaction dominate. But we are talking, and all the data I showed you before is related to a different regime. This is, again, the same spectrum, frequency, energy. But here, this is our regime. So the spectrum is continuous. We have this power law that we saw before. The energy here is orders of magnitude larger than the energy in this weak, very weak regime. And the question is, what's going on here compared to what's going on here? So the approach we take is to bring the system into steady state. We drive it with a specific intensity. Then for 1 second, we increase the injection of energy and bring it back to the steady state. And we follow, in our 3 dimensions, we measure the field in all the planes and study what happens to this wave packet. Because if it was not rotating, it would be just more intense and then probably diffuse. But remember, this is a wave packet of waves, and it travels. So this is height above the injection, 30 to 50. And this is time. And we can see this is the steady state here. And injection, the pulse arrives. There's some angle here which indicates a propagation velocity. And later on we will see reflections, etc., etc. So we measure it in real space. We also measure in K space, in wave number. So this is wave number. This is time. Now we integrate over the entire volume. And we see the steady state spectrum with a lot of energy in this K minus 5/3, right? A a lot of energy in small k, and this is the k minus thirds. And here, this droplet of energy which is not balanced with the steady state, we put it there and see what happens. That's the experiment. So we believe that if this perturbation is small, and if we can track these modes, it will tell us the story of what happens to those modes in the steady state. They will be representative modes for the steady state processes. So first of all, this pulse lives on the dispersion relation. This is not a big surprise, but it's important to notice. This is when we subtract the steady state energy spectrum and we take only the energy of the pulse. This is what we see. These are waves. They propagate. Now we get and do the following two processes. So in real space, it propagates as a wave packet of inertial waves. Not a big surprise, but remember, this is not in a steady, in a silent background. This is within turbulence. Now, we analyze what happens for different frequencies. So here there are examples of 3 different frequencies. Right? This is high frequency, more than the rotation rate, half of the rotation rate, and very low frequency. So high frequencies, we see their arrival. These sloped lines are the expected velocities for those frequencies under this rotation rate, etc. So yes, each mode of the injected energy propagates within the flow with the right velocity, but this mode, this nearly 2D mode, which we didn't inject because we inject high frequencies, it appears at a certain time. It grows. Those appear and decay and disappear. Now we can put all of these together into this plot. I will explain what it is. So here we have time. Here we have frequency. This is the cutoff frequency. So high frequencies, low frequencies. And here the color map is these are tricks of experimentalists. So in order to see all of it, for each frequency, we look for the peak and set it to be 1. So this intensity is not the same one as here. It is normalized to be 1 in order to be able to see it on the same plot. So what do we see? Several things. First of all, the arrival of these modes is consistent with the traveling of the inertial waves. The other thing is that within about 4 seconds, they decay. Energy was here. This thing is integrated over the entire volume. So there's not that energy passed through our sheet. It's simply gone. So within 4 seconds or so, it disappears. And if you remember the previous slide about the relevant nonlinear timescale from the broadening of the spectrum, if we put the numbers of this experiment there, we get 5 seconds. So the suggestion is that this dominant, most rapid process, nonlinear process in the steady state is the flattening of a mode down to this close to the 2-dimensional manifold. Right? The important thing is this is empty. Think of if there was a cascade in orientation, we would see how energy goes down here. It doesn't. It disappears, and as we saw before, it appears here. This grows. These disappear. So we suggest to describe it. So no cascade. Remember that frequency reflects orientation, right? So we suggest that there is some kind of a direct, very rapid, the most efficient nonlinear process in the system is a direct transfer of this 3D mode into this quasi 2D, and I insist on this quasi, and you will know why in 2-3 minutes. This is about frequency. Now about scales. What happens? The dynamics in wave number. So we subtract the steady state, and then we can track the additional energy of the pulse. We give it this identity of the pulse energy. This is questionable, but I think it is relatively okay and justified. So what we see, this is time, energy, wave number, injected energy. We saw something related to this earlier, but this time it is on existing turbulence. It's not a build-up. And we see the cascade down to the small scales. We can slice it in pre-selected places, and this is what we get, close to the injected time. So this is probably the injected profile of this pulse. And during the time, this additional energy travels to smaller and smaller wave numbers, and Omri analyzed the speed, the time evolution of this K star, and could show that it propagates as expected from an inverse cascade of energy. So it seems like, it looks like an ordinary 2D inverse cascade, consistent with what we saw at the beginning of the talk. However, this is what I said, that I'm not promising a good end, and this is my privilege as experimentalist. I say this is how the system behaves, now you think and try to explain it. So here is an interesting thing. We can not just integrate over the volume and make these cuts and see an inverse cascade like that. We have the information in Z. So once we look in Z, so for example, this is for a given wave, horizontal wave number, this is a short, like large wave number, we have a Z, the height, and time. So we see that it arrives at a given time, it travels upward, we see some kind of hints of reflections. The slope here is the predicted velocity for this mode, assuming or with very low frequency or close to 1, to 0. And fine, so this is the same thing that we saw as in the one-dimensional plot as a peak. This is it with Z information. We go to a smaller wave number, so it arrives a bit later. We see reflections of these waves. The slope is again the proper slope for this thing. And then we go to a lower wave number that we hardly injected. Remember that this pile of energy traveled from high wave number to inverse cascade, basically. But here we didn't nearly have energy injected. It appeared, okay, inverse cascade, but it is waves. Again, these are waves going up and down in the system. And if we go even further to smaller wave numbers, and even long time after injection, when this process of cascade is going on, these are still waves that go in the up and down in the system. And if Omri analyzes the dominant slopes in those pictures, this is what you get. Again, not a big surprise, but this is the velocity predicted for inertial waves of this wave number. So it means that the process of inverse cascade that we saw, which fits so well to the turbulence, it is not free of waves. Now, I don't want to say that waves mediate it, but they are there. You might say, well, big news, you must keep some kind of coherence, and so waves should do it. I agree. But it seems like considering wave dynamics and nearly two-dimensional modes. Okay, the frequency of all these waves is, for us, in our resolution, is as close to zero as possible. But it is not zero. We see them going up and down. And we can, no, this will take forever, I think, because I cannot drag the slider here. But I will put it in the background because this is the last slide. So here we see a height, and we see the the horizontal wave number in our volume. We will see the injection. We will see the inverse cascade, but we will see up and down propagation. So these are not perfectly 2D modes. And they are waves, and remember, they obey the same phenomenological power law in frequency and energy as their shorter friends, higher wave number modes. And so we will just see the beginning, and then I will finish. So this is the injected energy, and we will see it going to the left, but we will always distinct variations in Z going up and down, up and down. Unfortunately, our measurement cannot cover the entire tank. We would like to see it continuously, but so it goes up and down, and it travels, and eventually it will reach this point. So, conclusions. I will just flash them here. I would like to say that, yeah, we identified three different time scales in the system. One is the linear traveling time. And the other one, which is new, I think, for us and could be set quantitatively, is about 10 system rotation times in our case, which is this nearly flattening, but nearly only flattening of modes to this close to the manifold. And then there is an inverse cascade of energy, but we would like to say that according to what we see, this inverse cascade involves waves. And the main conclusion is that even beyond this very weak driving regime of three-wave interaction, which we saw, these triads, this is a different regime, more energetic, very definitely broad. Waves are important in this regime, so I don't know how to put together, this wave and quasi 2D mode together. And another thing is this question, which to some people that are not from this field might be, I don't know, not so important, but to some people it is, the question of this exact 2D manifold. In finite systems, it gives a lot of problems in describing this wave and 2D system together. In a finite system like ours, and like every system, basically, maybe we should not think so deep about this exact 2D, because it seems like the wave field gets as close as we wish to this 2D manifold. Thank you very much.
Thank you very much. Very, very interesting talk. So may I understand, so you have some asymmetry of propagation of inertial wave at some time domain and also spatial domain.
Yes, we drive the system from below.
Yeah.
There are many reflections. If we can show what a single pulse would do, it goes many times up and down when there's no turbulence. You could see that this is, as mentioned earlier, there is, like in internal waves, here you have two modes of helicity. Those, one would go up. This is more intensive than this. These are the downwards going. Okay. So there is a flux of energy from our source up. And you can see it by this difference. But there are waves going down as well. And I don't think that this is a very important, that the picture will be
Yeah, but if you have some asymmetry at some moment, then you certainly have a positive, I think negative helicity in small scales at some moment. Then I think the turbulent flow itself at that scale is not at all 2D. I think it's 3D. So then I think if you can measure helicity, so it gives some measure for 2D, 3D
I see.
ratio. So I think asymmetry of propagation of inertial wave is crucial, or inhomogeneity along the rotation direction, inhomogeneity of energy or anything.
So you think it is crucial for what part of the...
Yeah. Then if you have inverse cascade, it is not necessarily due to the effect.
I see.
Yeah, I think so.
Okay. Thank you.
So could you comment on the degree of locality or non-locality of what you call the slow inverse energy cascade? In other words, is this, we've seen examples in this meeting of things that look like conventional pictures of cascades with sort of small steps in K, and also very non-local transfer processes. And in particular with the waves, you wonder, the wave effects getting into the act, you might think the non-locality would creep in too.
Okay, so from what we could measure, in this horizontal K, there is locality. Once the energy is there in this, close to this 2D manifold, we could even, yes, maybe I should go quickly here. I think this is the best, the most relevant slide here, that yes, we see energy goes continuously in K in a kind of a cascade, in a local way. Well, I must say, maybe things, maybe the question is related to, maybe I should add information. If we drive the system very strongly, we do get this big condensate, and there could be some, I don't know, we never looked at it, but in mirror of things that we hear here, it makes sense to look for non-local transport. I don't know. Here in what those flows, this moderate driving that I described, I think it is local.
So you may be below the threshold for non-local.
Yes. Driving it stronger will alter the flow. You do get big vortex, and then things are different, and we haven't studied them thoroughly in that regime.
Yeah, so I'm just curious. So since it's experimental talk, I'll ask an experimental question. So, I mean, I appreciate your point about getting the angles, the closest angle to 90 degrees that you could get. And so it seems to me you have, that'll correspond to the largest wavelength in the Z direction. So you're going to have a windowing issue with your Fourier transforms.
Yes,
Yeah.
It is smaller. It gives us a smaller, if you talk about this uncertainty that the data sets are long. The data sets are...
Not long in time, but long in...
yes. Well, in space, then I might have a problem with the... Yeah,
That was my
system size,
question.
yes.
How big is that windowing effect on the scale of what we see in that crossing diagram? It's small. You're saying it's
not the effect. The system is, we do have this separation of scales, which is good enough, but for example, you saw some of the things that were with some spikes at high frequencies. For this, we applied kind of a windowing in K, but this is mainly for the high frequencies. Our system size is our system size. This is what we have. This is what we have. This either 80 centimeters on one slice or 30 centimeters on a 3-dimension. So it's not perfect. It's not the entire system. It's on the order of the system size, and this is what we have. Yes. Sorry. Yes.
Okay, so then a very naive question. And you can't tilt your observation plane, I mean, relative to the axis. You tilt your measurement planes relative to the axis to get the angles close to 90 degrees that are not 90 degrees.
Our illumination is from the lab while the system rotates.
Yeah, that's what I thought. Yeah,
So
okay,
this
yes,
would
right,
not
that
work. I can comment something that, yes, we cannot measure angles with high enough accuracy directly. But if we believe that the relation between frequency and angle holds, then this power law, not this one, but of omega, which goes to tenths of a hertz or even less, represents angles that are very, very, very shallow. But they are not zero. We saw that they still propagate. That's this thing.
I think we'll end here. Thank you very much again.